Ships operate in a highly aggressive chemical environment. Submerged, metallic structures face continuous degradation as the surrounding saltwater relentlessly attacks the exposed steel. This diagram illustrates natural galvanic corrosion. Inevitable paint defects expose the underlying steel to the environment. Here, seawater acts as an electrolyte. This conductive medium accelerates the transfer of electrons away from the steel, causing the metal to dissolve. The global shipping industry spends billions of dollars annually repairing this exact process. Left unchecked, this loss of mass leads to severe structural damage, reduced operational efficiency, and critical safety failures. To halt this deterioration, engineers employ cathodic protection. It alters the electrochemical behavior of a metal surface, supplying it with external electrons so that localized corrosion reactions physically cannot occur. Without actively managing this electrochemical reality, the structural integrity of any marine vessel is guaranteed to fail over time. The baseline solution is sacrificial anode cathodic protection, or SACP. A more reactive metal, like zinc, is attached to the steel. It dissolves to save the structure, relying on the natural galvanic difference between the metals to generate a protective current. However, passive sacrificial metals have a severe engineering limitation. They lack the voltage capacity and physical longevity to project a protective field over the massive, complex surface areas of modern commercial and naval warships. For large-scale maritime operations, the mandatory solution is impressed current cathodic protection, or ICCP. Instead of relying on passively degrading metals, an ICCP system uses a dedicated active power supply to forcefully drive the protective current through the water. Protecting massive naval vessels isn't solved by simply attaching reactive metal to the hull. It requires dynamic power distribution and active electronic control. This diagram shows the ICCP system as a closed electrical circuit. A DC power source forces a precise electrical current into the environment, artificially polarizing the entire structure. Looking at this schematic of a ship's hull architecture, we can map exactly how this circuit is integrated into the vessel. Direct current leaves the ship's internal power supply, known as the transformer rectifier, and travels outward to the external ICCP anodes mounted on the hull. These external anodes release current into the highly conductive seawater, distributing it directly into the submerged steel hull. The current then travels through the ship's metallic structure, flowing through return cables back to the negative terminal to complete the circuit. In this system, the anode itself does not dissolve. It acts strictly as the durable medium transmitting the electrical field into the water. By forcing this continuous electrical flow into the steel, the entire submerged structure becomes a protected cathode, completely immune to electrochemical dissolution. Driving that field requires the transformer rectifier, the central hardware component responsible for converting and regulating the ship's power. This schematic details the entry point. Standard high-voltage alternating current drawn directly from the ship's internal power grid enters the transformer. The transformer then steps down the voltage to match the lower voltage requirements necessary for the hull, adjusting based on ocean salinity and temperature. This chart shows the next phase. The rectifier bridge takes the stepped-down alternating current and transforms it into the direct current required for the electrochemical barrier. Internal filters then smooth the output, ensuring a steady, continuous pulse of DC power is delivered to the anodes. This precisely throttled direct current is the lifeblood of the protective field, providing the exact number of electrons needed to keep the steel stable. To deploy this power, ICCP anodes are mounted externally. They are installed in flush-mounted housings below the waterline to minimize hydrodynamic drag as the ship moves. Because they must endure continuous electrical discharge without degrading, these anodes are manufactured from highly specialized conductive materials like mixed metal oxide or platinized titanium. This diagram maps the necessity of multi-zone placement. A massive ship requires a carefully calculated array of anodes for uniform current distribution. Complex geometric areas, particularly the aft stern near the propellers, experience high turbulence, requiring highly targeted anode placement to maintain the field. If the current distribution is uneven, localized corrosion will still occur in the shadowed areas of the hull where the electrical field fails to reach. The physical layout of the anodes along the hull is as critical as the electrical power driving them. To confirm the hull is actually protected, the system must maintain a specific electrical potential relative to the seawater. For standard silver chloride setups, this target operational window is between -800 and -850 millivolts. To measure this, ships are equipped with reference electrodes, highly calibrated physical sensors installed along the hull alongside the anodes. The sole function of a reference electrode is to continuously measure the exact potential difference between the ship's steel hull and the surrounding electrolyte. Looking at an actual ICCP system log, we can see continuous readings pulled from the forward and aft reference electrodes. Values returning at 250 or 235 millivolts on a zinc reference scale confirm the hull is operating safely within the optimal green range. These millivolt readings are fed continuously into the Auto Control Unit, or ACU. The ACU is the microprocessor brain of the system. If the ship enters colder, more resistive water, the hull potential will drop. The ACU detects this instantly and automatically throttles the rectifier's output up, pushing more current to maintain the target voltage. This closed feedback loop transforms the ICCP from a simple power supply into an autonomous, reactive system that adjusts to ocean conditions in real time. The complete process flows linearly. AC power enters the rectifier, converts to DC current, exits through anodes into seawater, polarizes the hull, is measured by the reference electrode, and reported to the ACU. The ACU then instructs the rectifier to continuously adjust output. By permanently halting the chemical dissolution of the steel, this active loop drastically reduces the billions of dollars otherwise required for hull repairs and steel replacement. For naval vessels, this technical achievement translates directly into increased operational readiness.
Ships remain deployed and structurally sound, rather than sitting idle in maintenance facilities. Despite its automation, the physical hardware of the system still requires periodic inspection. During scheduled dry dock maintenance, engineers physically examine the anode coatings and reference electrodes for wear. Today, autonomous underwater vehicles, or AUVs, are increasingly deployed to perform these tasks while the ship remains in the water, mapping hull coatings and verifying ICCP anode integrity via camera and sensor arrays. Using robotic systems to monitor the cathodic protection grid removes the immediate need for human divers, expanding inspection capabilities and improving shipyard safety. The survival of a steel vessel in a saltwater environment requires constant power and precise measurement. Mastering marine electrochemistry and the robotics systems built to monitor it is the foundational requirement for modern naval engineering.